This is the morning related rates test review. Number one, helium is pumped into a spherical balloon at a constant rate of 25 cubic feet per minute. At what rate is the surface area of the balloon increasing at the moment when its radius is 8 feet? All right, the two equations we're going to have to use is volume of a sphere, which is v is equal to 4 over 3 pi r cubed, and then the surface area of a cube, of a sphere, is 4 pi r squared. All right, let's see what's provided for us in the problem here. Okay, helium is pumped into a spherical balloon at a constant rate of 25 cubic feet per minute. If we look at some context clues here around this number, we see cubic feet. So cubic feet is referring to volume per minute. We know that's sort of a rate. So we know this is going to be rate of change of volume with respect to time. And helium is being pumped into a spherical balloon. So that means the volume is going to be increasing as more helium is pumped into the balloon. So we know that this is going to be dV dt positive 25 cubic feet per minute. All right. At what rate is the surface area of the balloon increasing? So what the problem is asking for us to find is finding the rate of change. We see the word increasing. So the rate of change of the surface area. So we're looking for ds dt at the moment when the radius is 8 feet. All right, so we're working with two equations here, volume and surface area of a sphere. Let's just go ahead and find the derivative for both. So the derivative for v is going to be dv dt. 4/3 pi stays as 4/3 pi. Really, we're just trying to find the derivative for r cubed. So we go through power rule, bring down the 3, r squared dr dt. And when we bring down the 3 and the 3 in the denominator of the 4/3 will cancel out. So we're left with dv dt is equal to 4 pi r squared dr dt. Let's just go ahead and also find the surface area derivative. So s becomes ds dt. 4 pi stays. We just have to deal with this r squared. So the derivative for r squared is 2r dr dt. When that 2 comes down, the 2 and the 4 combines to be 8. So 8 pi r dr dt. All right, let's see what information we can figure out here. If we're trying to find ds dt, to find ds dt, we need r, which we do have, and we need dr dt. But to find dr dt, we need to go through our other equation, our rate of change of volume equation. Okay, so from this equation, we can arrive at the rate of change of the radius, and then from this point on, we can then plug in and find our last piece of missing information, which is ds dt. All right, so first thing, we need to find dr dt through the dv dt formula. So dv dt, rate of change of volume, gets replaced with 25 is equal to 4 pi r, radius is 8. That's given to us in the problem, 8 squared dr dt. So now we just divide all these terms over to the left side. 25 divided by, let's see, 8 squared times 4 will give us 64 times 4, which is 256. We divide that over, and then we reduce to find our isolated value for dr dt, which reduces to be, we'll leave it as 25 over 256 pi. So then this gets plugged in for dr dt from the surface area derivative equation. So dr dt gets replaced with 25 over 256. Radius r gets replaced with 8. And then we just use our calculator here to plug in 64 times 25 divided by 256, reduced to be 25 over 4 because the pi also cancels out. And this is surface area, so area unit of measure is going to be square feet, and then this is going to be with respect to time, so per minute. Okay, number 2, a spherical snowball with the outer layer of ice melts so that the volume of the snowball decreases at a rate of 2 cubic centimeters per minute. So we know that this number is referring to the rate of change of volume because we see the description of the volume. Snowball decreases, so the volume decreases at a rate. So we know dv dt is going to be assigned to this value, but we see the word decrease, so we know volume is decreasing, so we need to make the adjustment with the rate, meaning that dv dt must be a negative 2 cubic centimeters per minute. How fast is the radius changing when the diameter is 10 centimeters. So we're trying to find the rate of change of the radius. So we're trying to find dr dt. And then at the moment when the diameter is 10 centimeters, well, we don't really need diameter. What we do need is the radius. So we can just convert this to be when the radius of the snowball is 5 centimeters. So radius is 5 centimeters. All right, so we're given the rate of change of volume. We're asked to find what the rate of change of the radius. So let's just go ahead and start with an equation that will relate volume and radius. So volume and radius is v is equal to 4 over 3 pi r cubed. We find the derivative with respect to time for both sides of the equation. V becomes dv dt. 4/3 pi stays. We just need to find the derivative for r cubed, which is 3r squared dr dt. And then the 3 that comes down will cancel out with 3 in this denominator. So we're left with 4 pi r squared dr dt. All right, so now we just have to find dr dt. We know what the rate of change of volume is, which is -2. So we make that substitution. We know what radius is, which is given in the problem through the fact that the diameter is 10 centimeters. So replace r with 5, and then now we can solve for dr dt. So multiply all this out. 4 times 25 is 100. Pi divide this over to the other side. -2 over 100 is -1 over 50 pi, and then dr dt is feet per minute. Okay, number 3. Two cars moving from the same point. One travels south at 60 kilometers per hour. The other travels west at 25 meters per hour. So this the point with the 90-degree angle where these two sides meet at 90-degree angle is the starting point. So car X is moving to the left, car Y is moving down. At what rate is the distance between the cars increasing 2 hours later? So we're trying to find the rate of change of Z. We're trying to find the rate of change, the distance changing between X and Y at a given moment in time. Right, so we have an equation that relates these three lengths of the triangle, of this right triangle, which we can use using Pythagorean theorem. So horizontal squared plus vertical squared is equal to hypotenuse squared. So x squared plus y squared equals z squared. Once we have our equation, once we have the equation that relates the variables, we can then find the differential equation, find the derivative of each term. So x squared becomes 2x dx dt. Y squared becomes 2y dy dt. Z squared becomes 2z dz dt. All right, so one travels south at 60 kilometers per hour. Sorry, 60 miles per hour. The other travels west at 25 miles per hour. What's the distance between the cars 2 hours later? So let's think about where these cars are in relation to the starting point 2 hours later. So 2 hours later, that's a good hint for us to figure out, right? Because if a car is traveling 60 miles per hour south, then 1 hour he's going to cover 60 miles. The second hour is going to cover another 60 miles. So after 2 hours, the distance between the starting point and the current location for the vertical car will be 120 miles. Okay, so we'll let the distance y be 120. X, okay, it's traveling at 25 miles per hour. So after 1 hour, it'll be 25 miles from the starting point. After a second hour, it'll be 50 miles from the starting point. So we know the distance for X 2 hours later will be 50 miles from the starting point. So we have X and Y. We can then figure out Z going through Pythagorean theorem. X squared plus y squared equals z squared. If we solve for z, we can get z is equal to 130. We know what dx dt is. Dx dt is 25 miles per hour. dy dt is 60 miles per hour. Now, the direction has nothing to do with whether these values remain positive or negative. What we need to consider is what's happening to the lengths of these triangle horizontal and vertical component. Well, we know x is increasing over time, so that's why we have to represent dx dt as positive 25 miles per hour. The length of y is also increasing over time, and so because as the car travels further and further south, the distance between the car and the starting point will grow larger and larger. So we'll have to let the rate of change of y be represented by a positive rate, 60 miles per hour. So we have dx dt, we have dy dt, we have x, y, and we also have z from Pythagorean theorem. So that should be enough to fill in all the variables except for the one that we're trying to find, which is dz dt. So x and dx dt gets replaced, y and dy dt gets replaced, z gets replaced with 130, and then we just solve for dz dt. So combine those values together, divide both sides by this here 260, and then we get dz dt is equal to 65 miles per hour.